On behalf of the Vice Chancellor and Principal, Professor Nana Poko, it gives me a great pleasure to welcome you to the inaugural lecture of Professor Molla Demlie. The Vice Chancellor conveys his congratulations and best wishes to Professor Molla Demlie. The Registrar, Professor Kathy Gleland, conveys her apologies and congratulates Professor Demlie on his promotions and thanks him for his contribution to the School of Agricultural, Earth and Environmental Sciences. I would like to acknowledge the following guests this afternoon: members of Council, members of Executive Management, members of Senate, our inaugurant this afternoon, Professor Molla Demlie, family and friends of Professor Demlie, academics, professional staff, alumni, and distinguished guests. A special welcome to our guests from universities and organizations within South Africa, African continent, and across the globe. Inaugural lectures form part of the University Public Lecture Series and may only be presented by newly appointed full professors who have appointed in academic school and centers. Inaugural lectures represent an opportunity for showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic career, providing official recognitions of their promotions or appointment to full professorship. These lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their own contributions to their field, to academic peers, students, research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievement with his or her family, friends, mentors, and colleagues. Distinguished guests, it is my pleasure to now introduce the Dean and Head of School of Agriculture, Earth and Water Sciences, Professor Julius Sibiya, who will now formally introduce the inaugurant, Professor Molla Demlie. Over to you, Julia.
Thank you, Prof. A very good afternoon to all our viewers joining us from wherever you are joining us from. I have the honor this afternoon to introduce our inaugurant, Professor Molla Demlie. Professor Molla Demlie is a full professor in the discipline of geological sciences in the College of Agriculture, Engineering and Science at the University of KwaZulu-Natal, based in Durban, South Africa. Professor Molla received his BSc in Geology and MSc in Hydrogeology degrees in 1992 and 2000, respectively, from the University of Addis Ababa in Ethiopia. And he received his PhD degree in Hydrogeology in 2007 from the Department of Applied Geology, Ruhr, University of Bochum in Germany. His PhD study was supported by a scholarship award received from the German Academic Exchange Service, DAAD. Professor Demlie joined the Department of Applied Geology, Bekele University, in early 2001 as a lecturer and served as head of the department for 2 years until end of 2002. He joined the School of Geological Sciences, UKZN, Durban, South Africa in 2007 as a lecturer immediately after completing his PhD. He has been serving UKZN at various capacities: lecturer from 2007 to 2009, senior lecturer from 2010 to 2018, associate professor from 2019 to 2022, and full professor from August 2022 onwards. He has been the academic leader of the discipline of geological sciences in the School of Agricultural, Earth and Environmental Sciences since February 2022. Professor Demlie's research area is hydrogeology, in particular, hydrogeological system analysis, hydrological processes, groundwater surface water interactions, conceptual and numerical groundwater flow and contaminant transport modeling, response of groundwater to land use and climate change and urban hydrogeology. He has successfully supervised 3 doctoral PhD, 22 master MSc, and more than 70 honors students, and published over 60 research articles in peer-reviewed conference proceedings in Scopus and ISI index journals, published by different publishers ranging from Elsevier, Springer, and others. He is currently supervising 7 doctoral students and 3 MSc students. Professor Demlie has examined a number of MSc and PhD theses from universities in South Africa and Botswana. He is a member of the editorial board of the South African Journal of Geology and has served as guest editor for the Journal of Hydrology. He is a reviewer for more than 15 high-impact factor journals, such as Journal of Hydrology, Hydrological Processes, amongst others. Professor Demlie has been invited as a speaker at a number of international conferences and workshops, including Canada, Cameroon, South Africa, amongst others. Professor Demlie is a National Research Foundation rated scientist, C3, since 2019. He has been serving as a member of Professional Steering Committee for a number of projects of the Department of Water Affairs and Sanitation, Research Proposal Reviewer for WRC and NRF, Reviewer and Evaluations of Scholarly Books and Conference Proceedings. He is currently leading 3 major research projects funded by the Water Research Commission, WRC, and the South African Medical Research Council. Professor Demlie is a member of the Groundwater Division of the Geological Society of South Africa and International Association of Hydrogeologists, the African Groundwater Network, and a registered member of the South African Council for Natural Science Professional. Professor Demlie, I invite you to deliver your lecture.
Thank you very much, Professor Julia, and thank you very much, listeners. Gustus, it gives me a very great pleasure to present some of the highlights of our research, particularly the research projects that I have been leading. My talk today, as part of this inaugural lecture, is Groundwater, a strategic resource beyond contributing to our water supply mix. The outline of my presentation briefly is I'll introduce the notion of groundwater as a resource, groundwater as a source of urban and rural water supply from sole source to water supply mix, groundwater in the water, food, energy, and ecosystem nexus, groundwater from a resilient resource to vulnerability, and I will conclude my presentation at the end of the lecture. When we talk about groundwater, groundwater is part of the greater water resources.
Sorry,
and
Prof, you are not sharing your slides?
Okay. Apologies for the technical glitch. So my presentation is on groundwater. Groundwater as a strategic resource beyond contributing to our water mix. The outline of my presentation is as follows: introducing groundwater. Groundwater as a source of urban and rural water supply, both as a sole source and in the water supply mix. And also the role of groundwater in the water, food, energy, and ecosystem nexus. Groundwater from a resilient resource to vulnerability. And I'll end up the lecture by putting some concluding remarks. Groundwater as part of the major water resources that we have on the planet Earth. Planet Earth, or Mother Earth, is uniquely situated in the pressure-temperature phase diagram of water, where water occurs in 3 phases only on Mother Earth. As you can see from the figure, all of the planets, the sister planets of our Mother Earth, that occurs actually beyond our planet Earth, water occurs either in the vapor form or in the solid ice form. So our water, including groundwater, is actually uniquely positioned and occurs only on Earth. So this is very, very fascinating. And that's why actually Mother Earth is, for now, the only place that we humans can thrive. Groundwater in the water resources framework is the only freshwater next to the ice caps that gives us the largest freshwater resources on planet Earth. If you can see, 97% of the water we have on the planet is saline, that is stored in our oceans. And the remaining ones, groundwater, makes up around 30% of the freshwater resource, while the 68.7% is inaccessible, and these days actually also subjected to melting due to global climate change. On the surface water side, rivers, swamps, and lakes constitute only 2% of the freshwater resources that we have. So groundwater is one of actually the largest and the vast freshwater resource and freshwater source that is easily available around where we live. Groundwater, when we talk about it, we don't see it. And some says it is a resource out of mind because it is out of sight. But as hydrogeologists and groundwater practitioners, and because actually groundwater is a very strategic resource, we unravel the hidden resource through a number of specialized research and practice methodologies and approach. Anyhow, groundwater occurs invariably within the pore spaces of fractures or fractured rocks or pore spaces of geological formations known as aquifers. So aquifers are subsurface geological formations that have the capacity to store, transmit groundwater in an appreciable amount. So groundwater is not actually water that occurs in a subterranean lake. It occurs within geological materials. The occurrence of groundwater in a particular region is determined by a number of factors. Among them, the climate of the region, the distribution of the lithology and stratigraphy of the different geological units, and the geological structure of the strata that the groundwater resides. If we, for example, compare the nation Germany and Namibia, because of their location and also their climate, groundwater in Namibia occurs in a very deeper depths and flows practically to the ocean, not really discharged into mainly into surface water system like streams because of its depth. While in Germany, because of the nature of the climate, wet relatively higher moisture in the atmosphere, gets more precipitation and less evaporation compared to the landscape of Namibia, then groundwater occurs at a shallow depths, sustaining even at, in some cases, groundwater-dependent plants and other species. In other areas, groundwater occurs also in cavernous structures, particularly in dolomitic and limestone terrains. One of the large springs in a crust terrain that I indicated on the left side of this slide shows you how much groundwater flows underground within some karst aquifer systems in carbonate formations. To give you a brief account of the groundwater use estimate taken from the National Groundwater Association, groundwater is the world's most extracted raw material. And the extraction rate is estimated to be 982 kilometers square per year. You can see the volume of water being extracted. It is more than oil, more than other base metals. About 70% of the groundwater withdrawn worldwide is used for agriculture. So groundwater has a major contribution to our food security, and in the water food energy security also, it plays very, very important role. Groundwater also provides almost half of the drinking water worldwide, particularly in wetter areas, because groundwater occurs at shallower depths. Groundwater used to be actually the sole source of water supply. In other areas, it plays actually in a role in the water supply mix. From a global context, 38% of irrigated lands are equipped with irrigation that can actually source groundwater from shallow to intermediate depths. So groundwater, a very, very important resource, which must be protected. From an African perspective, this map shows you the storage potential of subsurface aquifers across Africa. And as you can see, actually, some areas have paleo waters that has been recharged in drier, wetter region, water times, such as actually in the Pleistocene period, 50,000 years ago. A very good example is actually the Libyan desert, where modern day groundwater recharge or modern day precipitation is almost nil, but they have groundwater reserves that are stored in sandstone aquifers. But modern day, this water is not renewable because modern day recharge is zero. This estimate takes into account the area of the land, the saturated thickness of the aquifers or the subsurface water storage units, and the porosity. Because of that, this is an overestimate because groundwater storage is estimated not based on porosity, but rather based on either specific yield or storativity. A specific yield for unconfined aquifers and storativity for confined aquifers. So the actual volume of groundwater that we have across Africa is much lesser than actually the one reported in here. If you see the place in this estimate, the place is of South Africa. South Africa has also a huge groundwater storage from which actually even the renewable amount is also quite large. So as a nation, we have both renewable groundwater and groundwater that is actually in storage for many years. Comparing our water resources in South Africa, the total annual runoff South Africa generates is estimated to be around 34 billion cubic meters. However, the mean groundwater storage based on specific yield estimated recently by the Department of Water Affairs Groundwater Resources Assessment Project to put it at 235 billion meter cube. From this, the renewable groundwater is around 19 billion. So compared to surface water that can be developed, the amount of groundwater that we have across the country is a huge amount. And if you compare it with the previous estimate that I tried to show, to depict here, the two are quite different, and the difference in the estimation is the parameters that is used. So the actual groundwater storage that we have in South Africa and the renewable part, which is annually recharged from rainfall, is around 19 billion. So that's the right and the correct number. And this implies that our groundwater storage in South Africa is more than 7 times bigger than the total surface water resource that we have. On top of that, this water resource has already been developed. Only small pocket areas are yet to be developed. So the groundwater will become actually a strategic resource that will offset any water supply deficit going forward. Now, our research is trying to unhide the hidden resource. And the following are our main research focus areas for the last 10 years. This includes water supply sustainability and water quality are very, very important issues. In this case, our research focus concentrates on the groundwater supply sustainability and also making sure that our groundwater quality is maintained, protected, and improved as we go further. Another area of our research is surface water groundwater interactions at various scales and land uses, including urban catchments, because groundwater is a unique resource that drives in some regions the occurrence of wetlands, the occurrence of lakes, and at the same time, it maintains the low flow of major and small rivers across the South Africa landscape and beyond. An additional research focus area that my team has been busy is understanding the response of groundwater to climate change and the role of groundwater also in adapting climate change effects. This slide shows you groundwater use in a rural setting. On the left side, groundwater pumping from a hand-operated borehole. It's an intermediate borehole, having a maximum of around 30 meters below the ground level. And on the right side, you see actually the another well, which is hand-operated, but this well is much deeper than the left one. The right side is from the Ethiopian highlands, a community water supply well. You can see operated using the AfriDev pump. And on the left side, this is from the coastal plain of KwaZulu-Natal, where communities are tapping the shallow groundwater for their water supply. So groundwater is an important resource that supplies not only rural communities, but major towns. At least what I'm trying to show you here is the source of rural water supply can come actually from shallow to intermediate depths without even the use of energy. That means without the use of motorized submersible pumps. On the other side, this is in South Africa. The right borehole is in the coastal plain of South Africa next to the Indian Ocean. And on the left side, this is from KwaZulu-Natal Midlands. Both boreholes supply the community with water. You can see actually groundwater pumped actually from the borehole is stored in those JoJo tanks and supplies the community. On the other hand is the submersible pump, and this pump pumps water and supplies the community along the northern KwaZulu-Natal coastline. This is typical actually. The geology or the aquifer type in both areas are quite different. This borehole taps groundwater from shallow to intermediate depths, and the geology is from unconsolidated materials, which we call them actually recent deposits. On the other hand, this borehole is tapping groundwater from a fractured and weathered aquifer from the Natal group sandstone. So this is a very good comparison where groundwater occurs in primary pore spaces on the right side and in secondary pore spaces on the left side. Taking you to urban water supply at a very early times of my research, I was part of the team who used to investigate the groundwater supply for the city of Addis Ababa. That's my PhD also. My PhD study was done actually under that project. This is the one of the water supply wells for the city of Addis Ababa. So groundwater can supply at least a portion of the water supply of a mega multi-million population like the Addis Ababa city. So this is a major project. You can see it, the pipes and this is one of actually very large boreholes that tap water from the aquifer. So this is the aquifer underlying this flat plain. The Akaki plain is coming actually from the weathered and fractured scoraceous basalt, which is a completely different material than the one that I showed you earlier. So this is a volcanic material which acts as an aquifer and supplying water to the city. The catchment that gives recharge to the well field, the Akaki well field, which I tried to show you, is equipped with a number of meteorological stations that will help us in estimating the amount of actually renewable groundwater or the amount of recharge that goes into the aquifer. So rainfall recharge is coming from rainfall, and based on actually the long-term data from the 1990s all the way to 2020, we have analyzed the trend, we have estimated the recharge rate, and the result of this recharge analysis is published in the Journal of Environmental Earth Sciences. Furthermore, we investigated and modeled the capacity of the well field. Unfortunately, because of the demand and supply imbalance, groundwater in that particular well field has been declining, which, as you can see actually from the piezometers, the monitoring boreholes, and also from the pumping boreholes. So how much recharge that we have actually, because we can't access all of the recharge, one can access all of the recharge, and it may not reach also the aquifer in a short period of time. So there is a disconnect and imbalance between pumping and recharge that leads to a substantial groundwater level decline, which I'll come to that at a later stage. However, we defined the groundwater flow directions, as you can see, based on a number of measuring groundwater level measuring points, including actually also characterizing the chemical or the hydrochemical quality of the groundwater. And the result of this research has been published in the Journal of Hydrology, one of our mainstream high impact factor journal. Groundwater in the water food energy nexus. As I said, groundwater is a key water supply source. And some areas it is the sole supply of water, and in other areas like in Addis, it is supplying water actually, and adds support to the surface water sources. In this figure, you see actually springs that are helping the local community for garden irrigation. And this shows you that groundwater in the form of springs can supply water for small-scale holders, thereby creating the food security, and on the other side, it is creating also jobs. We support those farmers through water quality analysis and also in understanding the source of the spring water. Recently, we drilled a borehole to supply the community and to make actually the spring water actually more sustainable, because the spring has a limited discharge that will actually irrigate land. So the spring and the groundwater that we drilled to a depth of 100 meters have the same sources. So they have the same characteristics in terms of environmental isotopes. They are recharged from modern day rainfall. And this actually is a very good result. So that actually smallholder farmers are using a renewable water source, which actually will be sustainable. So actually the amount of hectareage or the land size can be limited. Groundwater also plays an important role in achieving the UN Sustainable Development Goals, that is the UN Agenda 2030. It's not only limited actually to meeting the 17 goals. At least it meets around 4 of the Sustainable Development Goals: clean water supply, good water, good health, and zero hunger in terms of food security, and so on and so forth. So if we secure water to our community, especially to the vulnerable community, especially the disadvantaged community, then they can turn actually their life around and they prosper. And you can say actually they will be happy. These kids in rural Africa are going for fetching water actually from a groundwater source. So in that context, actually clean water supply and sanitation is secured. And in areas where actually this water is used for irrigation, then food security is also achieved. Some highlights from our research across, particularly the eastern side of the country, especially in KwaZulu-Natal province. We have studied a number of areas. One major area of study is the largest coastal aquifer in South Africa, the Maptoland Coastal Plain Aquifer, or sometimes we call it the Northern Zululand Plain Coastal Aquifer. This aquifer, as you can see on the digital elevation model, this region is situated along the Indian Ocean coast, and it is made up of geological materials that are from recent to the Cretaceous period. This aquifer is known to have the largest groundwater as a primary aquifer storage in South Africa. And this aquifer is known, we know that also it drives actually the ecology. This area is made up of wetlands. You can see also it's the Isimangali Nature Reserve. There are lakes, wetlands, and then all of these lakes and wetlands are driven or supplied from groundwater, because there is no major stream, at least the northern half of this coastal plain. As a result, groundwater, if it's not used sustainably, because actually it is maintaining the local ecology, that actually, if it is affected and if it is polluted, and also it is depleted, the ecological consequence is very, very serious. As a result, we have to, one, study it, two, try to identify actually what's going on, the balance between abstraction from different sources and also the allowable renewable resource. That will lead us to some of these results. Groundwater, we know that from our study using various integrated hydrogeological techniques, we found out that groundwater and wetlands and lakes are intricately connected to the extent that groundwater is the driver of the ecology. This study shows that the groundwater, most of the streams that flow across this coastal plain is coming from groundwater, and so does also the lake or the lakes. These in particular, the Lake Sibaya system. So environmental isotopes, hydrogeochemistry, groundwater levels, Richard estimation, all this gives us characterizing the aquifer and understanding it. If we understand it, then we can take actually mitigation measures if there are some negative consequences of over abstraction. Most of this work is published in respected journals like the Journal of African Earth Sciences. We have published also our work in the Journal of Geochemical Exploration, particularly this paper, the Journal of the paper from the Journal of Geochemical Exploration deals with actually trying to improve an iron-rich groundwater in the coastal plain for those rural communities, because groundwater in some areas of this coastal plain occurs in redox conditions, and when we pump it out, the groundwater becomes rich in iron, and this iron has to be removed, otherwise the aesthetic quality of the water is not good, and people, especially the local people, will abandon it. So the local people, to use that water, we devised this a very simple method of filtering water and removing iron. Another research area is the coastal areas around Durban. We have looked at various groundwater resource and then its dependence on whether actually land, because of a land use change in an urban setting, groundwater will be vulnerable to pollution and over abstraction. So in this particular region, we identified the groundwater flow distribution, and groundwater both actually in the northern coastal plain and also in the greater Durban region is acting as a barrier and pushing salt water towards the ocean. So the salt water, freshwater interface is pushed towards the ocean so that our groundwater reservoirs and aquifers stay fresh until the time comes actually the over abstraction will reverse the hydraulic gradient, so that salt water flows inland. That should be also mitigated through some industry charge methods. This part of our research, particularly the papers on the Natal group sandstone, and also the paper that we published on the hydrogeology for the Durban metropolitan region, has a wider readership because of actually also the limited amount of information that we have in this region. So we are contributing to the knowledge base, and at the same time actually we are creating actually the groundwork so that in future actually we're going to model actually different scenarios, including climate change and also land use change. Groundwater is not only a resource that plays a very important role in the water supply mix, or as a sole source of water supply, or as a driver of the ecology, as I try to explain it in the coastal plain aquifer. Groundwater also plays a major role in the economy by creating really local tourism, especially groundwater, thermal groundwater coming deeper sources. They are known to have therapeutic properties, and the temperature, the high temperature, means that it can be used as spas, creating actually more jobs in the local environment. I'll try to demonstrate this recreational or tourism role of groundwater and groundwater as a therapeutic resource, particularly in some areas of KwaZulu-Natal. But South Africa is endowed with so many thermal springs which are being used locally as spas, creating the local tourism economy to flourish. I tried to do a research on at least 5 of the thermal springs that are found in and around the province. And from this research, you can see the thermal spring distribution in the central northern parts of KwaZulu-Natal province, where we are staying. And some of the springs are developed as spas. This is one of the well-developed one, is a Natal spa, thermal spring, which serves the communities and tourists. And also the Tangami or Black Mfolozi thermal spring is also used as a spa. However, at least during the research period, the Shushu spring, which lies along the Tugela River, and also the Lilani River, the Lilani thermal springs that lies also east of Greytown. Though there is a limited recreational value, but they are not actually fully developed. So fully developing these resources means that actually creating more jobs, and that leads actually to economic revival for this particular region. The temperature variation and the chemical characteristics of this water means that typically our environmental isotope, chemical studies show that actually these thermal springs are coming from deeper sources. So they are older than modern recent waters, but their age is more than at least 50 years, which puts them actually to not very old, but at least older waters. But these waters are not halio waters, but they are actually linked to modern day meteoric water. That means they are recharged from rainfall from the local region. But the depths of circulation and the geothermal gradient means that when this water circulates from deeper sources and comes to the surface, the temperature increases, and they are used as a spas and so on and so forth. But this integrated technique has unraveled actually the typical scientific characteristics of this thermal water. So we have estimated the depth of circulation of this groundwater from recharge, that means from surface source, down to the deepest part of the reservoir, that means the aquifer. So the depth of circulation is on average around 500 meters, but for some, it can go up to 1,000 meters below ground, particularly for the Shishu thermal springs. I have tried to estimate the reservoir temperature, the temperature at depths, and the temperature of the thermal spring when it comes or when it daylight to the surface are quite different. So I used different types of sodium potassium geothermometers to estimate the reservoir temperature. And if the reservoir temperature is higher, we can even use actually this resource for local energy generation. So the temperature of the reservoirs, the maximum temperature we found is around 150 degrees Celsius at depth. That means at the bottom part of the aquifer that stores this resource. In that case, actually, there is a potential that we can use this some of these reservoirs for local energy generation as well. In addition to the religious, recreational values, groundwater has also religious and therapeutic values. This small church is in the Ethiopian highlands in Addis, just outside of Addis, where a spring is revered by the church to have a therapeutic or healing ability. So it attracts a number of spiritual followers of the church to get healed actually from this this holy spring. So groundwater has not only economic value, but it has also religious value. It has also health implications as well. Where and how the therapeutic nature of the water coming from is still debatable. Now, I tried to show the groundwater as a very important and strategic resource. Then this strategic resource is not limited actually to supplying water as a water mix, as I said. I try to demonstrate that it can also supply water as a sole source, or it can drive the ecology, leading actually to the food, water food energy nexus. I try to show you. But recent urbanization, land use change is deteriorating the water that is relatively resilient and of high quality compared to surface water is becoming actually threatened and becoming vulnerable to human-induced water quality degradation. This is one of my colleague assisting me in the sampling of water and testing water in the field. And you can see actually this borehole is sitting next to a petrol station, and the water samples that we got out of this groundwater borehole is completely polluted by the derivatives of this refined oil. So in urban areas, it is highly affected by anthropogenic activities. These two plots shows you also groundwater being polluted by nitrate and chloride in the central Addis Ababa region, the metropolitan region. And south of actually this sampling point is the main water supply wellfield exists actually. So a gradual movement of this high nitrate water towards a wellfield means that the groundwater source for the city will be threatened until otherwise actually mitigation measures are taken. In addition to that, this is a plot of groundwater data from the Greater Durban region. And similarly, the Greater Durban region, groundwater is being affected actually by leachate coming out of the different waste storage facilities or landfills, including radioactive waste like tritium. You can see it actually. The salinity versus tritium plot shows you high tritium content is a very good indicator of groundwater being affected by leachate coming or released actually from particularly the dysfunctional landfill sites. This is not at the end actually. The region is actually highly industrialized also, and that means that actually if we can't actually protect the groundwater from leachate generated from landfill, then the other industrial pollution will be very dire. So groundwater resource, the groundwater quality is not the only problem that we are facing, particularly in Eastern South Africa. Groundwater storage is also being threatened. One, because of land use change, leading actually to overexploitation through a number of large-scale pine plantations, over-abstraction of groundwater without actually proper regulation and monitoring, and also to do with actual aspects of climate change or reduced rainfall that would otherwise reach the groundwater as a recharge. Our research shows that groundwater, particularly across KwaZulu-Natal province, is threatened actually by over-abstraction and land use changes. And so the storage depletion is apparent. We tried to link the statistical data we found from aquifer depletion across the province with meteorological drought. And it is clear that part of this groundwater depletion is also as a result of the reduction in the long-term rainfall pattern across the province. The results are published in a number of high-impact journals, and particularly the groundwater storage depletion was estimated using also remotely sensed data, using the GRACE satellite system, using statistical techniques from in situ measurements. And also, we have checked the land use change, particularly the northern coastal plain, and it's very clear that our groundwater resources are depleting. Both shows the evidence is very, very clear. So we have to do some management intervention. This two cluster shows you the first map plot shows you the reduction of lake level, particularly Lake Sibaya in the northern coastal plain of South Africa. And the second one, the lower one, is a borehole showing actually a downward trend, telling you a groundwater level reduction leading to actually storage depletion in the coastal aquifer. This storage depletion, because groundwater is intricately linked actually to these surface water systems, including wetlands and lakes, can say actually it is also translated actually impacting the lake as well. So it's not the only reason, because the lake is also subjected to overpumping. Meteorological drought calculations for the last 30, 40 years shows actually that drier spells are more frequent than wetter spells across the province. And this is also one cause of groundwater and lake level reduction. So there are a number of factors that work in tandem to affect our groundwater and surface water resources. The groundwater storage depletion, at least in the Lesotho to Mlatsi water management area, is found to be actually very direct, but especially for the primary aquifer. Nearly in 20 years, 1 billion meter cube of water has been lost actually from groundwater storage in the primary aquifer. In the secondary aquifer, the loss is much higher because of also the larger in area. Nearly 3.5 billion cubic meter of groundwater storage has been lost in the, so the sum is actually nearly 4.5 billion cubic meters of groundwater storage is lost in only one water management area in northeastern South Africa. So to protect our water resource, the only way is for groundwater to be sustainable. The only way is through integrated water resource management. This water resource management, particularly when integrate the social side, the environmental side, the economical side, the governance side, and the public participation side, when it comes together, we can safely and sustainably manage our water resources, especially our groundwater resources, which is a very strategic resource for now and for our future generation. So in conclusion, groundwater as a key component of the environment plays a very important role beyond as the water supply mix. However, it is threatened by storage depletion as a result of a number of factors, and also quality deterioration, mainly as a result of anthropogenic factors, which can be through proper legislation and also compliance, we can arrest them. And aspects of climate change is also driving this water storage depletion and quality deterioration. So the integrated water resource management is a key for sustainability of both groundwater and surface water resources. It plays key role in climate change adaptation. It is obvious because groundwater is more resilient. At the same time, it has a larger storage capacity. So through managed aquifer recharge in wetter seasons, one can use actually more surface groundwater during dry season. So this integrated water resource management means that it includes also managed aquifer recharge, and also this managed aquifer recharge, particularly along the coastline, will protect our groundwater resource from sea level rise and consequent seawater intrusion. Groundwater science is evolving, and it is becoming actually increasingly towards interdisciplinary in nature. So moving forward, all of actually the components that are listed in here actually, like hydrologists, chemists, nutrient specialists, biologists, ecologists, erosion specialists, sedimentologists, all of them must come together actually do the research. Thank you very much, and I would like to use this opportunity to thank the following people. Professor Stefan Wonlich of the Ruhr University of Bochum, who is my mentor and my PhD supervisor. Professor Tenala Mayeno of Addis Ababa University, who was my master's supervisor also, who introduced me to the science and the world of hydrogeology. Colleagues and fellow researchers whom I collaborate and continue to collaborate and learn. Current and past my students who have contributed also to the knowledge base that we are trying to establish. And in the end, I would like to thank all my family members for their support for doing actually my busy research endeavors. Thank you very much. Thank you.
All right. Thank you so much, Professor Demlie. You can put down your presentation. On behalf of the University Senate and the Vice Chancellor, Professor Nana Poko, and the Registrar, Kathy Cleland, we're so proud of you to be part of UKZN and the contribution of the science that you have done that contributes around the University of KwaZulu-Natal. This is a very engaged type of scholarship, which as a university we are so proud of. We want to wish you all the best and your family for the support that they've provided for you when you're doing these studies, including our colleagues and your mentors and your students. On behalf, once again, of the university, we are so proud of you and keep up of doing a good job. We wish you all the best in your future career. Be with us forever, and we're so proud of you. Thank you very much. Demlie, thank you so much. It's time for weekend. All the best.